Have you ever noticed how much of reality hides in plain sight? The air you breathe, the water that bends light, the warmth that moves between molecules. None of it is visible, yet all of it runs the show. Chemistry works quietly in that hidden layer, balancing gases in the sky, shaping the motion of atoms, and setting the pace of every reaction that keeps life steady. Even light itself, from ultraviolet to microwaves, plays by those invisible rules. The closer we look, the more we find that the unseen isn't empty, it's everything. If you like exploring what lies beneath the visible world, a quick like and subscribe helps others discover it too. Settle in, and let's explore the chemistry of the invisible. The world we move through feels solid and clear. Surfaces look still, colors shine, and the air seems empty. Yet almost everything that makes this familiar world work happens beyond what we can see. The chemistry of the invisible operates in silence, underneath every sense. Molecules move, collide, and react constantly, forming the hidden framework that keeps our lives balanced. What we call visible reality is only a thin surface laid over a much deeper structure of motion and energy. Human senses, as sharp as they are, capture only a fraction of what exists. The eye sees light between roughly 380 and 740 nanometers in wavelength, a narrow slice of the electromagnetic spectrum. That small band contains all the colors we know, yet most light lies outside it. Ultraviolet light, invisible to us, burns skin and powers reactions in the upper atmosphere. Infrared radiation, which we feel as warmth, moves around us every moment, but goes unseen. Bees can see ultraviolet patterns on flowers that guide them to nectar. Snakes detect infrared heat to find prey in the dark. Humans live in a modest window of color and call it the whole sky. Our sense of smell reaches a little farther into the invisible. The nose can detect some compounds at just a few parts per billion, a trace so small that a single drop could scent an entire room. Yet oxygen, the gas that fills our lungs and fuels every heartbeat, has no smell at all. Countless molecules pass by us unnoticed, either too faint, too stable, or too common for our receptors to catch. The same is true for touch. Skin can tell smooth from rough, warm from cold, but cannot feel the motion of atoms or the vibration of individual bonds inside a crystal. We live tuned for comfort, not for molecular detail. That limit creates an illusion, the illusion of nothing. When you hold your hand out, the space between it and the world feels empty. In truth, it is dense with nitrogen, oxygen, argon, carbon dioxide, and water vapor. Each molecule rushes and spins, colliding hundreds of times every second. Their motion creates air pressure, carries sound, drives weather, and shapes climate. What feels still is only calm at our scale. In the microscopic view, air is a storm of motion. Even clarity is a kind of invisibility. When light passes through a material instead of being absorbed or scattered, we call it transparent. The difference between a cloud and a sheet of glass lies not in what they are made of, but in how they handle light. A cloud's droplets scatter light in all directions, turning it white. Glass, with its regular atomic structure, lets visible light pass through almost unchanged, leaving only a faint reflection. Visibility depends on how matter absorbs, transmits, or scatters light, the quiet conversation between waves and particles. Even substances that seem colorless have preferences. Pure water absorbs red light slightly more than blue, giving deep water its soft tint. Air itself scatters blue light more effectively than red, which is why the daytime sky glows blue and sunsets fade into amber. Not all invisibility comes from light. Sometimes it comes from dilution. A few drops of dye in a lake vanish from view, not because they are gone, but because they have spread too thin to notice. The same happens with a scent. A single puff of perfume fills a room, but as the molecules drift apart, the smell fades even though every particle is still there. Chemists describe this in parts per million or parts per billion units for what cannot be seen but still exists. 1 part per billion is like a single grain of sand among 1,000 tons of beach. Many natural systems work at this level. Ozone protecting the upper atmosphere, trace metals in seawater, or hormones circulating in blood. Each acts in concentrations too low for sight, but too important to ignore. There is also invisibility shaped by time. Some chemical reactions are so slow that, to human eyes, they appear motionless. Iron rusting in the corner of a shed, limestone dissolving in rain, organic matter turning to soil, all unfold at a pace beyond everyday notice. If time was sped up, metals would seem to fade, rocks would flow, and oceans would shift color as quiet reactions rippled through them. What we call stillness is often motion we can't see. Even a stone resting on a ledge vibrates on an atomic level. Its atoms stretch, compress, and trade energy with the air billions of times each second. To call it lifeless is only to admit that we can't see fast enough or small enough to notice the dance. Invisible chemistry runs every part of daily life. It carries heat away from cooling tea, releases flavors from food, and corrodes metal bridges over years. The air you breathe, the light that warms your skin, the slow aging of everything around you, all depend on reactions happening silently. What seems like nothing is rarely empty. Even the clearest air and purest glass are filled with motion. Light bends as it travels through them. Atoms shift and vibrate. Molecules share energy in endless exchange. The visible world is the surface glow of a much larger process. Air, for instance, feels weightless and still. You can wave your hand through it, yet it never resists. But on the molecular scale, it is crowded beyond imagining. Billions of particles move in every cubic centimeter, colliding and rebounding hundreds of times each second. Each molecule dances at its own pace. The lighter ones, hydrogen, helium, move fastest. The heavier ones, oxygen, carbon dioxide, move slower, all together, forming a steady hum of motion. Despite this activity, air is remarkably stable. About 78% is nitrogen, 21% is oxygen, just under 1% is argon, and a tiny fraction, roughly 0.04%, is carbon dioxide. The rest is a delicate mix of neon, helium, methane, ozone, and other trace gases. That tiny amount of carbon dioxide, small enough to hide in decimals, helps keep the planet warm and feeds plants through photosynthesis. It regulates temperature and connects the carbon cycle that links ocean, land, and sky. To chemists, these proportions describe a masterpiece of balance. Nitrogen is the quiet majority, steady, patient, and mostly unreactive. Each nitrogen molecule holds 2 atoms bound by one of the strongest triple bonds in nature. That bond makes it reluctant to react, but when broken by lightning, certain bacteria, or industrial processes, nitrogen turns into compounds like ammonia and nitrates that nourish plants. Without this rare event, ecosystems would starve. Nitrogen, though calm, holds the keys to life's supply chain. Oxygen, in contrast, is eager and active. It reacts quickly, joining with other elements to release energy. Combustion, rusting, and breathing all rely on its hunger for bonds. When oxygen meets carbon and hydrogen, as in wood or food, it forms stable oxides and gives off heat. Every breath you take draws oxygen inward to fuel this exchange, trading it for carbon dioxide that your body produces. The air you exhale is warmer, wetter, and about 4% carbon dioxide, a sign of invisible chemistry at work. Argon, the third major gas, is the opposite of reactive. It belongs to the noble gases, a family so stable they rarely form compounds. Argon drifts through the air unchanged, the same atom from the birth of the planet still moving through your lungs today. It passes through generations, through animals, volcanoes, and storms, untouched by chemistry, a silent witness in every breath. Carbon dioxide, though scarce, plays an outsized role. It is transparent to visible light, but absorbs infrared radiation, trapping heat and warming the surface of the Earth. The climate depends on this invisible balance. Too little and the planet freezes. Too much and it overheats. Water vapor joins in, shifting constantly between gas, liquid, and ice. It can make up anywhere from 0 to 4% of the atmosphere, depending on temperature and humidity. As warm air rises and cools, water vapor condenses, releasing heat that drives weather systems. Even when the sky looks clear, this invisible vapor shapes how warm or cool the air feels against your skin. Humidity is chemistry in motion. It measures how many water molecules float among the nitrogen and oxygen ones. A humid night feels heavy, not because the air is thicker. It changes little in density, but because water absorbs and holds heat, slowing how quickly air cools. That same property makes fog, mist, and steam so soothing. It's the chemistry of comfort. Beneath all of it is a simple principle known as Dalton's law. In a mixture of gases, each one behaves as though it alone fills the entire space. Every gas keeps its own pressure, coexisting in balance with the others. It's a quiet, invisible agreement that makes the air steady and breathable, a calm layer of order holding together a restless world. That agreement has weight. The total pressure we feel at sea level, about 101 kilopascals, is the sum of countless molecular pushes, each gas adding its share to the whole. Nitrogen, oxygen, argon, carbon dioxide, all press outward as if alone, yet together they create the steady weight of the atmosphere. This shared balance lets us breathe with ease, inflate balloons, cook at reliable temperatures, and send airplanes skyward. It keeps flames steady, lungs working, and weather alive. Even the air in a still room is alive with motion. Every breath you take shifts its chemistry. The air you exhale holds water vapor, carbon dioxide, and faint traces of compounds like acetone and ethanol, tiny signatures of metabolism. These drift outward and mix invisibly through diffusion, blending into the larger pool of gases. Sometimes, in a beam of sunlight, you can see specks of dust floating lazily. Yet each mote is enormous compared with the molecules moving all around it. The true dance of air is silent, colorless, and unending. Despite its lightness, air carries weight, a column of it stretching from the ground to space above every square meter of Earth weighs about 10 metric tons. That unseen pressure presses in all directions at once, keeping water from boiling away and giving shape to weather and life. Without it, the oceans would evaporate, our blood would fizz with bubbles, and the sky would fall still. The air's steady push keeps the world in equilibrium, holding warmth, liquid, and motion in place. Sometimes, the chemistry of the atmosphere makes itself known through scent. The sharp smell before a thunderstorm comes from ozone and nitrogen oxides forged by lightning. The earthy freshness after rain, called petrichor, rises from oils released by soil microbes and lifted into the air by tiny bubbles in wet ground. The sea's clean edge comes from sulfur compounds escaping from waves. Each aroma is a reminder that the air is not empty. It is a messenger carrying the chemistry of Earth. You can imagine it again as a great ballroom filled with endless dancers. Nitrogen holds the rhythm, oxygen spins energetically, water vapor weaves between partners, and argon drifts in quiet observation. Temperature and humidity set the pace, while sunlight conducts from above. The performance never stops. Air may feel like nothing, but it holds everything. It links every breath you take to forests, oceans, and all who came before. The faint breeze on your skin is a tide of molecules connecting you to the entire planet, a chemical continuity that never ends. Water shares this same quiet complexity. It looks simple, clear, soft, and harmless, but its behavior is one of nature's most intricate designs. Every drop hides invisible architecture, tiny electric charges, shifting bonds, and subtle fields that give it extraordinary power. The secret begins with shape. A water molecule has one oxygen atom joined to two hydrogens in a bent form, like a small boomerang. Because oxygen pulls electrons closer to itself, it becomes slightly negative, while the hydrogen ends turn slightly positive. This uneven charge makes the molecule polar, each one a tiny magnet that attracts and repels others. Billions of these molecules cling together with delicate hydrogen bonds, weak individually, but strong in number. These bonds break and reform countless times a second, giving water both flexibility and cohesion. Polarity also makes water a superb solvent. Drop salt into it, and the crystal lattice quickly falls apart. The positive sodium ions draw oxygen atoms toward them. The negative chloride ions attract the hydrogens. Water wraps around each ion, forming protective shells that keep them apart. To the eye, the salt vanishes, but in truth it becomes a suspension of charged particles moving freely. These ions carry electricity. Pure water alone conducts poorly, but in reality, it is never pure for long. It collects ions from air, soil, and every surface it touches. Those ions, sodium, calcium, magnesium, and many more let current pass and give water its quiet vitality. Inside the body, similar ions act as electrolytes, enabling nerves to send signals, muscles to contract, and hearts to beat. Even without impurities, water constantly rearranges itself. A tiny fraction of its molecules split into hydrogen and hydroxide ions through a process called autoionization. The balance between them defines the pH, a scale that measures acidity and basicity. In pure water, the concentration of hydrogen ions is 1 in 10 million, giving a pH of 7 neutral. Each step on this logarithmic scale represents a 10-fold change. A pH of 6 is 10 times more acidic than neutral. A pH of 8 is 10 times more basic. Life depends on this narrow range. Enzymes, the catalysts that drive biology, work only within specific pH conditions. Human blood, for example, must stay near 7.4. Stray too far, and the chemistry of life begins to fail. Water rarely keeps balance alone. It relies on buffers, mixtures of weak acids, and bases that resist sudden shifts in pH. When extra hydrogen ions appear, the base component absorbs them. When hydroxide ions rise, the acid side donates protons to restore order. Buffers act as gentle moderators, ensuring stability amid change. The body's bicarbonate buffer is one of the most elegant examples. Carbonic acid and bicarbonate ions in the blood maintain pH through a subtle feedback loop. Holding your breath raises carbon dioxide levels, forming more carbonic acid and lowering pH. Breathing faster removes that acid, restoring equilibrium. It is an invisible dialogue between lungs and blood, keeping every cell alive through balance. The oceans use a similar conversation. When carbon dioxide dissolves in seawater, it forms carbonic acid, which can split into bicarbonate and carbonate ions. Together, these compounds create a vast buffering system that keeps ocean pH steady and protects marine life. Without this safeguard, shells and coral made of calcium carbonate would slowly dissolve. For millions of years, the ocean's chemistry has guarded that balance, though increasing carbon dioxide from the atmosphere now strains its capacity. Still, the buffering system continues its quiet defense, one ion exchange at a time. Buffers also shape smaller corners of life. Saliva neutralizes acidity after eating, protecting teeth. Lakes resist swings in pH caused by rainfall. Even swimming pools depend on buffers to stay gentle on skin and eyes. Everywhere water appears, it carries this instinct for balance, keeping systems stable yet responsive. The strength of water lies in its paradox. It is both soft and powerful, reactive yet calm. It dissolves mountains grain by grain and cushions fragile cells within living beings. Its transparency hides restless activity, hydrogen bonds forming and breaking, ions drifting, and molecules exchanging energy in a ceaseless flow. Every sip of water holds this invisible performance, a network of forces keeping matter in motion without chaos. Drop a little ink into a still glass of water, and the lesson becomes visible. The color begins as a concentrated twist, then unfurls, thinning as it spreads until the water turns evenly tinted. No stirring, no force, only the gentle spread of particles moving from crowded regions to empty ones. This is diffusion, the quiet choreography of chemistry that prevents the universe from ever standing still. Diffusion is easiest to grasp by watching something even smaller. In 1827, the botanist Robert Brown observed pollen grains floating in water through a microscope. He saw them jitter and dance, even in perfectly still liquid. At first, he thought the motion came from life itself, but when he tried dust and other lifeless particles, the trembling remained. Life was not the cause. Decades later, Albert Einstein explained why. Each grain was being struck by water molecules in constant motion, colliding randomly from all sides. These impacts made the particles wobble endlessly. This phenomenon, called Brownian motion, became the first visible proof that atoms and molecules truly exist. Diffusion is Brownian motion seen from a wider view. It describes how particles naturally drift from crowded regions to emptier ones, driven only by random motion. The ink cloud in water, the aroma of bread spreading through a kitchen, or the warmth from tea fading into the air, all follow this same law of dispersal. If you could shrink down to the scale of a molecule, the world would look chaotic. You'd be knocked and jostled from every direction, bouncing in a zigzag path that never repeats. But when billions of molecules move this way, their random actions form a steady pattern. Chemists describe it simply: particles move down their concentration gradient until equilibrium is reached. It is order emerging from randomness, the signature of a universe that never rests. Diffusion explains how smells travel, how heat spreads, and how gases mix in the air. It governs the delivery of oxygen into your bloodstream and the escape of carbon dioxide as you breathe. It carries nutrients through soil and currents through oceans. Every gentle change in the world, fading color, softening scent, slow cooling, is diffusion at work. It is the patient bridge between stillness and motion, a reminder that even when things seem at rest, chemistry continues its endless conversation just beyond sight. That conversation has its tempo. Temperature quietly sets the rhythm of diffusion, deciding how quickly molecules wander and how eagerly they mingle. It is not just a feeling of warmth or cold, but a measure of molecular speed. When heat rises, molecules gain energy, collide more often, and mix more easily. Cold slows them down, leaving motion sluggish and hesitant. A sugar cube takes its time to dissolve in iced tea, but vanishes almost instantly in a hot cup. Heat doesn't add color or texture. It adds motion energy, made invisible. Each degree marks a faster rhythm in the constant hum of matter. Diffusion never stops. It only changes pace. In the lungs, diffusion becomes life itself. Oxygen slips through the thin membranes of tiny air sacs into the bloodstream, while carbon dioxide moves the other way to be released with each breath. In the leaves of plants, the same trade happens in reverse. Carbon dioxide flows inward for photosynthesis. Oxygen drifts outward to the open air. Smell, too, is born from diffusion. When a jar of coffee is opened, its aroma spreads as millions of molecules wander outward, colliding and bouncing through the air until the entire room fills with the scent. It feels like magic, but it is simply mathematics and motion, the natural search for balance. In kitchens, diffusion works as the invisible artist behind flavor. As soup simmers, compounds from vegetables and herbs drift outward, meeting and mixing in the gentle flow of liquid. It softens fruit in syrup, draws salt evenly through a brine, and spreads aroma from a pot of tea. Nothing in cooking truly stands still. Even when the pot is silent, molecules are exploring. Diffusion blurs edges and turns separation into harmony. The same principle explains the spread of heat. When you hold a mug of hot chocolate, warmth moves by diffusion from the air to your skin. Faster-moving molecules bump into slower ones, sharing energy until everything reaches a comfortable balance. It's why a cold room slowly warms after you light a fire. Energy seeps outward through countless collisions, spreading evenly without hurry or noise. Inside the body, diffusion keeps thought alive. Ions drift through channels in neurons, carrying tiny electrical pulses. Across microscopic gaps, neurotransmitters diffuse to deliver signals from one cell to another. The ideas forming in your mind rely on diffusion moving at molecular speed. Even memory depends on these quiet exchanges. Chemistry in motion, shaping awareness, one molecule at a time. Einstein's explanation of Brownian motion turned this soft process into something measurable. It proved that atoms and molecules were real and allowed scientists to estimate Avogadro's number, connecting the invisible to the countable. A century later, the same principle guides studies of nanoparticles, viruses, and fine dust, suspended in air or water. The random dance of matter that once puzzled a botanist now helps scientists model pollution, study protein folding, and track particles inside living cells. The restless motion of molecules has become a lens into worlds too small to see. Diffusion carries a certain patience. It never forces its way forward. It trusts time. It works through randomness, not strength. Left long enough, it always finds balance. The ink in the glass will keep spreading until every molecule has visited every corner it can reach. Each step of that journey is accidental, yet the outcome is inevitable. Even in stillness, the world keeps adjusting itself. Heat evens out, gases mix, colors fade, and balance quietly returns. There's comfort in that rhythm. Diffusion assures us that motion and calm are not opposites. The same slow dance that equalizes air in a room also smooths the boundaries of galaxies. The light from stars spreads across space for billions of years, obeying the same principle: movement toward balance. Diffusion is one of nature's simplest laws and one of its most universal. When you see steam curling from a cup, a scent drifting through a hallway, or color thinning gently through water, you're watching molecules meander toward harmony. It's motion without intent, progress without effort. Even thought behaves this way. Ideas spreading through the mind like dye through water. No clear path, only the peace that comes when everything has found its place. The universe, with all its storms and noise, still seeks equilibrium. Every push meets a pull. Every change calls for correction. This quiet conversation between forces is what chemists call equilibrium. It isn't a frozen pause. It's an ongoing negotiation. A tug of war so balanced that both sides move at once. Every chemical reaction has two directions: a forward path that forms new products, and a reverse path that rebuilds what was lost. At first, the forward reaction surges ahead, creating new compounds. As those compounds accumulate, some begin to fall apart again, drifting backward. Over time, both directions balance. Molecules trade sides endlessly, yet the overall composition stays steady. This moment when everything moves but nothing seems to change is chemical equilibrium. You can see it in simple places. The gas above a bottle of soda is in equilibrium with the fizz below. Carbon dioxide dissolves into the liquid and escapes back into the air at equal rates. Open the bottle and the pressure drops, breaking the balance. The bubbles rise not from chaos, but from the system seeking a new harmony. Chemistry dislikes extremes. It always looks for the middle ground. One of its clearest rules for this process is called Le Chatelier's principle. It states that when a system in equilibrium is disturbed, it shifts in whatever direction helps undo the disturbance. If temperature, pressure, or concentration changes, the chemistry quietly adjusts to soften the effect. A living example lies in the blood. Hemoglobin, the molecule that carries oxygen, binds it tightly in the lungs, where oxygen levels are high, then releases it in the muscles where it's scarce. The equilibrium between oxygen and hemoglobin changes with the surroundings affected by temperature, carbon dioxide, and acidity. When carbon dioxide rises or pH falls, hemoglobin's grip loosens, releasing oxygen where it's needed most. When conditions reverse, it binds oxygen again. Each breath is a cycle of equilibrium, shifting back and forth, moment to moment. The same principle steadies the oceans. When carbon dioxide enters seawater, it forms carbonic acid, which can split into bicarbonate and carbonate ions. These reversible reactions build a buffer that stabilizes ocean pH. If more carbon dioxide dissolves, part of it stays as gas, part becomes acid, and part transforms into other ions, all working together to prevent large swings in acidity. Without this balance, the calcium carbonate shells of marine life would slowly dissolve. Equilibrium keeps the ocean alive. You can find similar examples at home. Blow air into a glass of water, and carbon dioxide forms carbonic acid, lowering pH. Leave it alone and the gas escapes, restoring neutrality. Open a bottle of ammonia cleaner, and the smell floods out as the gas escapes solution. Seal it, and it quietly dissolves again. Equilibrium hides in the ordinary, maintaining order without announcement. Chemists describe these states with a value called the equilibrium constant, K. It represents the ratio between products and reactants when balance is reached. A large K means the reaction leans forward. A small one favors the reverse. These numbers guide processes from cloud formation to metabolism. They are the quiet mathematics of balance, the unseen rules, deciding which side of a molecular conversation speaks louder. Equilibrium gives chemistry its patience. Imagine two teams pulling on opposite ends of a rope over a bridge. Neither side wins, yet the rope stays taut. The bridge doesn't break. It holds steady through tension. That invisible tension is equilibrium. It's not stillness, but controlled motion. Every pull answered by another. Temperature and pressure can tip the balance. Heat added to a system may drive it toward reactions that absorb energy. Cooling may favor those that release it. Compress a gas, and the equilibrium shifts toward fewer gas molecules, easing the pressure. These adjustments happen instinctively, restoring calm with every change. In the atmosphere, equilibrium maintains the exchange between oxygen and carbon dioxide across plants, oceans, and animals. Photosynthesis and respiration form a global conversation, each breath and each leaf adjusting the balance. The air you exhale today might feed a tree tomorrow, which in turn releases oxygen back into the cycle. Even metals show this quiet pursuit of balance. Iron left outside reacts with air and moisture, forming a layer of rust. That surface crust slows further change, creating a local equilibrium. Silver tarnish behaves the same way, darkening until it finds its point of rest. Everything in nature, from the smallest reaction to the drift of continents, leans toward equilibrium. Push a system too far, and it resists. Disturb its balance, and it adapts. This is not stubbornness, it's resilience. It's why ecosystems recover after storms, why living bodies maintain homeostasis, why planets hold steady orbits. Equilibrium keeps change from breaking the world apart. It proves that stability doesn't mean stopping. Molecules keep moving, trading energy and partners, yet their numbers remain steady. From a distance, that motion looks like calm, but beneath it, everything is alive with exchange. The world isn't peaceful because it stands still. It's peaceful because every part moves just enough in both directions. In that invisible balance between change and constancy lies endurance, the art of remaining the same by never truly resting. Every chemical reaction follows that rule, yet some happen in the blink of an eye, and others take years. A match bursts into flame. Iron rusts over decades. The difference isn't in desire atoms always seek new bonds, but in the barriers between them. Each reaction faces a hill to climb, a threshold called activation energy. Picture two valleys divided by a ridge. Reactants begin in one valley. Products rest in the other. To cross between them, molecules must gather enough energy to reach the top. Only those moving fast enough or colliding just right make it over and continue down the other side. The rest bounce back, waiting for another chance. This is why heat has such influence. Temperature raises the energy of molecules, making more of them fast enough to climb that barrier. The higher the temperature, the more collisions succeed, and the quicker the reaction unfolds. Every flicker of a flame, every breath of wind, every heartbeat is chemistry powered by this exchange between energy and motion. That relationship between heat and speed is more than a metaphor. It's measurable. As temperature rises, the invisible world quickens. Molecules gain energy, move faster, and more of them reach the threshold needed to react. The change is not linear, but exponential. Each degree of warmth multiplies the odds of successful collisions more than the one before. Early in the 20th century, the Swedish chemist Svante Arrhenius captured this pattern in an equation that still defines chemical kinetics today. His formula revealed that even a slight increase in temperature can cause a dramatic surge in reaction rate. Heat doesn't just stir things, it amplifies the chances of transformation. You can see this law of motion everywhere. Bread dough rises more quickly in a warm kitchen because the enzymes in yeast work faster when energized by heat. Milk spoils sooner on a hot day because bacterial metabolism races ahead. Even metal rusts more rapidly in the summer, as atoms exchange electrons with greater ease. Heat quickens chemistry, cold slows it down. Refrigeration is simply controlled laziness for molecules, a way to make reactions fall asleep. Still, temperature isn't always enough. Some reactions remain stubborn, waiting ages for change because their activation barrier is too steep. That is where catalysts appear, the quiet facilitators of chemistry. A catalyst doesn't alter where a reaction begins or ends. It doesn't add energy or take any away. It changes the route. Imagine two valleys separated by a mountain ridge. The reactants rest in one valley, the products in the other. A catalyst opens a lower pass between them, a shortcut that needs less energy to cross. The start and end remain the same, but the journey becomes easier. Catalysts make this possible by stabilizing transitional forms, brief, unstable states between reactants and products. They hold molecules in just the right orientation for bonding or loosen old bonds that need to break. Once the reaction completes, the catalyst releases unchanged, ready to guide the next set of travelers. It doesn't wear out or get consumed. It simply repeats its assistance again and again. Nature has been using catalysts since long before humans knew the word. Every cell in every living thing relies on enzymes, nature's specialized catalysts, to keep its chemistry running smoothly. Each enzyme has a unique shape tailored to its target molecule. When that molecule, called the substrate, fits into the enzyme's active site, the enzyme bends or stretches it slightly, weakening certain bonds and encouraging others to form. The reaction that might take years on its own happens in fractions of a second. Some enzymes even adjust their shape as they work, a mechanism known as induced fit. It's less a rigid lock and more a handshake that adjusts until it feels perfect. These biological catalysts are astonishingly efficient. One molecule of the enzyme catalase can break apart millions of hydrogen peroxide molecules every second. Without enzymes, life's chemistry would be too slow to sustain life itself. Digestion, respiration, and DNA replication would crawl. Enzymes compress impossible timescales into workable rhythms, turning potential into pulse. Every heartbeat, breath, and thought depends on them. Humans, learning from nature, have created their own catalysts to serve industry. One of the most important examples is the Haber-Bosch process, developed in the early 1900s. It uses an iron-based catalyst to unite nitrogen from the air with hydrogen to form ammonia. This single reaction sustains modern agriculture, providing the foundation for nitrogen fertilizers that feed billions. The chemistry is simple. Nitrogen plus hydrogen yields ammonia. But without the catalyst, nitrogen's triple bond is too strong to break efficiently. The catalyst lowers that barrier, turning an impossible reaction into a practical one. Catalysts also clean the air. Inside car exhaust systems, catalytic converters use metals like platinum, palladium, and rhodium to transform carbon monoxide and nitrogen oxides into less harmful compounds. On their metallic surfaces, molecules land, rearrange, and depart as cleaner products. The transformation happens continuously and silently, a steady exchange between fuel, air, and chemistry that keeps urban air breathable. In the food industry, catalysts guide subtle transformations. Nickel and platinum catalysts help hydrogenate vegetable oils, changing liquid fats into smooth spreads and pastries. Others refine crude oil into usable fuels, form plastics, or assist in the synthesis of medicines. Almost every modern material owes something to catalysis, a hidden craft shaping what we eat, wear, and build. Yet catalysts are not magic. They cannot make the impossible possible. They only speed what nature already allows. They lower barriers, but they cannot remove the need for energy or change the direction favored by equilibrium. A reaction that absorbs heat will still require heat. One that releases energy will still do so. Catalysts only smooth the path. The study of how fast reactions happen, kinetics, is the science of time in chemistry. Two reactions might produce the same final products, yet one flashes in an instant, while the other creeps along for years. The difference lies not in the result, but in the pace of progress. Catalysts are like guides on that journey, revealing easier routes through the landscape of energy. In nature, kinetics and equilibrium exist together, like rhythm and melody in a song. Kinetics determines the tempo of change. Equilibrium sets the final note. Without kinetics, reactions would never reach balance. Without equilibrium, motion would have no destination. Together, they make chemistry both dynamic and dependable. A system always moving, yet always oriented toward harmony. Every reaction has its own personality, its own patience. Some burst forward with explosive enthusiasm. Others prefer the slow certainty of time. A match igniting, iron rusting, mountains eroding, stars forging heavier elements. Each is an expression of the same mathematical truth: motion meeting energy. Catalysts act as caretakers of that process, making sure transformation happens with efficiency rather than struggle. They show that progress doesn't need to be forced. It can simply be guided. The world around us is full of these quiet accelerators at work. When you see dough rising, a candle burning, or metal dulling in the rain, you're witnessing kinetics in conversation, the dance of atoms negotiating new partnerships. Somewhere in that conversation, catalysts whisper directions, shaping the outcome without ever taking credit. They are the conductors of the unseen orchestra of reactions, ensuring that chemistry keeps its rhythm without chaos. Light, too, plays the role of a catalyst, though in its own unique way. It carries no mass and makes no sound, yet it has the power to twist molecules, split bonds, and spark new combinations. Most of its activity lies beyond what our eyes can see. The rainbow we know, red through violet, is just a sliver of a much wider spectrum, stretching from ultraviolet to infrared and beyond. To understand light is to understand how energy moves through space without touch, how photons, those tiny packets of electromagnetic energy, shape the chemical world. Each photon carries energy that depends on its wavelength. Shorter wavelengths, like ultraviolet light, have higher energy. Longer wavelengths, like infrared or microwaves, have less. The shorter the wavelength, the greater the ability to rearrange or break chemical bonds. This connection between energy and wavelength defines the scope of light's chemistry, its power to destroy, to create, or to warm. At the energetic end lies ultraviolet light, invisible yet familiar to anyone who has felt a sunburn. These photons carry enough energy to damage DNA and alter proteins, but they also build. High in the atmosphere, ultraviolet light strikes oxygen molecules, splitting them into individual atoms. Some of these recombine to form ozone, 3 oxygen atoms bound together. That ozone layer then absorbs much of the incoming ultraviolet radiation, forming a shield born from the energy it tempers. Ultraviolet light also drives the formation of vitamin D in the skin. When certain cholesterol-like molecules absorb ultraviolet photons, they transform into precursors of this essential nutrient, supporting bones and immune health. In balance, ultraviolet light is both destroyer and creator, sculptor and healer, a paradox of chemistry and light. Move down the spectrum to visible and near-infrared light, and energy softens into the range that sustains life. Here, photons are tuned for photosynthesis, the process by which plants convert sunlight into chemical fuel. Chlorophyll molecules absorb red and blue light while reflecting green, giving leaves their color. Each absorbed photon excites an electron, sending energy cascading through a chain of reactions that split water, release oxygen, and store sunlight as sugars. Every forest, meadow, and blade of grass performs this controlled photochemistry every day, weaving light into life. Humans have imitated this process with solar technology. In solar panels, photons strike semiconductor materials, freeing electrons that flow as electric current. Artificial photochemistry transforms sunlight into electricity, echoing the work that plants began billions of years ago. Beyond the visible lies the infrared region, a domain of warmth rather than brightness. We cannot see infrared light, but we feel it as heat from a fire, a cup of coffee, or the sun-warmed ground. Infrared light doesn't break bonds, it makes them vibrate. Each chemical bond behaves like a spring between atoms, stretching and bending as it absorbs infrared energy. Every molecule has its own pattern of vibration, a unique spectral fingerprint. Scientists use infrared spectroscopy to read those patterns and identify substances, listening to molecular vibrations too slow for sight and too fast for sound. Infrared light also shapes the planet's climate. Molecules such as carbon dioxide, methane, and water vapor absorb and re-emit infrared energy, trapping heat within the atmosphere. This greenhouse effect keeps Earth warm enough for life. Without it, the planet would be frozen. With too much, it overheats. Infrared radiation is the planet's quiet thermostat, moderating between extremes. At even longer wavelengths are microwaves, carriers of gentle energy that favor rotation rather than vibration. They don't have the strength to break bonds, but can make polar molecules like water rotate rapidly. generating heat through friction. Microwave ovens harness this property, warming food from the inside as water molecules turn millions of times per second. It's chemistry, guided by rhythm, energy delivered invisibly, evenly, and without flame. Across the spectrum, each kind of light speaks to matter in its own language. Ultraviolet light reveals by breaking. Visible and near-infrared light builds and powers life. Infrared warms and measures. Microwaves stir softly. Together, they form a complete dialogue between energy and matter. Light's passage through the unseen is quiet, yet powerful. It scatters in raindrops to create rainbows, bends through air to color the sky, and penetrates skin to start the chemistry of life. The universe is written in this language of photons, a story told without words, where each wavelength adds a line of meaning to the endless conversation between energy and matter. Yet for all that light's eloquence, we hear only part of its speech. Most of the light that shapes our lives never reaches our eyes. It moves through air and water without notice, guiding energy between atoms, tracing the warmth that keeps oceans liquid and skies blue. Visible light is only a thin melody in a much larger song. Ultraviolet, infrared, and microwave light form the harmonies that give it depth. Together, they remind us that sight captures only a fragment of the universe's full performance. The invisible wavelengths carry most of the energy, most of the warmth, and much of the chemistry that keeps the planet alive. When sunlight touches your skin or steam rises from a cup, you are meeting just the surface of a deeper exchange. Beyond that visible glow, unseen light continues its quiet labor building, healing, and sustaining. It is the hidden chemist of the cosmos, forever turning energy into form and warmth into life. What the eye misses, science seeks to translate. Chemistry depends on the ability to see without sight, to listen to matter itself. The colors we perceive are only the beginning. The real drama of bonds forming and breaking happens too quickly, too small, and too subtly for any human sense. To reach that world, chemists have invented tools that let light, magnetism, and motion speak in their place. These instruments don't produce pictures in the usual sense. Instead, they turn invisible events into spectra, peaks, and patterns, a language of lines that describes how atoms behave when no one is watching. Spectroscopy is the art of turning invisible energy into knowledge. Every molecule, like a tiny instrument, vibrates and resonates at its own natural frequencies. When light or radiation passes through a sample, certain wavelengths are absorbed or scattered, producing a distinctive fingerprint. From that fingerprint, chemists learn what elements are present, how they are bonded, and how the molecule moves. It is not the chemistry of sight, but of listening. Infrared spectroscopy is among the most graceful of these methods. Each chemical bond acts like a spring connecting two atoms, stretching and bending in rhythm. When infrared light passes through matter, specific wavelengths are absorbed to make those tiny springs move. Each bond type, carbon-hydrogen, carbon-oxygen, nitrogen, or hydrogen, responds to its own unique frequency, or the resulting spectrum is a pattern of valleys that record those vibrations. Reading it is like hearing a chord and recognizing the instrument that played it. Raman spectroscopy offers a complementary approach. Instead of tracking which light gets absorbed, it listens to how light scatters. A laser beam strikes a sample, and most photons bounce back unchanged. But a small fraction gain or lose energy while interacting with molecular vibrations. returning slightly shifted in wavelength. Those minute shifts reveal the same vibrational signatures as infrared spectroscopy, but from a different angle. Raman spectroscopy is gentle, ideal for studying fragile materials, pigments, or even living cells without harm. Move higher in energy, and ultraviolet and visible spectroscopy take over. Here, photons excite electrons to higher energy states. When light passes through a colored compound, certain wavelengths are absorbed while others pass through or reflect back. The pattern of absorption reveals the electronic structure, the arrangement of electrons around atoms. Metals, dyes, and pigments owe their color to these transitions. A chemist can distinguish copper from cobalt simply by how each absorbs light. The same principle measures concentration. The more light absorbed, the more molecules present. It's the science behind tinted glass, but done with lasers and detectors instead of eyes. Fluorescence brings another layer of conversation. Some molecules, after absorbing high-energy light, relax by emitting photons of a longer wavelength. Ultraviolet light goes in, visible light comes out. The result is a soft glow, a signature both beautiful and precise. Fluorescent spectroscopy allows scientists to trace pollutants, follow biological molecules, and observe the motion of proteins inside cells. When a microscopic image shines green or red, it's chemistry translating invisible reactions into visible color. Beyond light, magnetism also speaks the language of the unseen. Nuclear magnetic resonance, or NMR, uses powerful magnetic fields to explore the tiny magnetic moments of atomic nuclei. When placed in such a field, certain nuclei like hydrogen or carbon 1,3 align with or against the magnet. A short pulse of radio waves nudges them, and as they relax, they emit faint signals determined by their chemical surroundings. Those signals reveal how atoms are connected, their neighbors, and even their 3D arrangement. NMR works patiently, mapping molecules from small organic compounds to complex proteins. It's the quiet detective of chemistry, slow but unerring. Mass spectrometry, by contrast, listens to motion. It ionizes molecules, accelerating them through an electric field and separating them by mass. Heavy ions travel more slowly, light ones faster, and their arrival times form peaks on a graph. Each peak represents a fragment of the molecule, allowing chemists to reconstruct the original structure. It's molecular archaeology, reading the broken pieces to understand the whole. The sensitivity is astonishing. Instruments can detect compounds at parts per billion, finding a single trace in an ocean of molecules. All of these techniques face the same challenge: separating signal from noise. Real data are never perfect. There are always fluctuations, stray vibrations, and tiny distortions from the environment. The difference between clarity and confusion lies in the signal-to-noise ratio, how strongly the real information rises above background hum. Scientists coax faint signals upward through better detectors, longer measurements, and careful calibration. Patience becomes part of the experiment. Sometimes the truth emerges only after hours of quiet waiting, as weak peaks sharpen and steady. Calibration itself is an act of discipline. Instruments are tested with known standards to verify accuracy. A blank sample containing only the solvent or background is measured first. Subtracting that baseline from the sample's data isolates what truly belongs to the molecule. It's a kind of chemical mindfulness, a reminder that meaning requires awareness of what is not meaningful. In this work, error is not failure, but context. Every measurement includes uncertainty, and the mark of a good scientist is not to erase it, but to understand it. Repetition brings confidence. When a peak appears at the same place in repeated trials, it graduates from possibility to fact. Precision in chemistry isn't about pretending the world is certain. It's about quantifying doubt until it becomes manageable. The payoff for such patience is extraordinary. Modern spectroscopy can uncover what was never meant to be seen. A test of drinking water can reveal a contaminant at a concentration of a few parts per billion, like finding a single drop of dye in an Olympic swimming pool. These discoveries protect health, ensure purity, and remind us how deeply connected we are to the chemistry of our environment. Sensitivity turns into responsibility. Seeing the unseen becomes a form of care. There is a rhythm to this kind of science. Instruments hum softly. Samples rest in clear glass cuvettes. Data emerge line by line. Each point, another word in the story. The chemist waits, interprets, and listens. It's a calm partnership between curiosity and patience. The reward is understanding, built from whispers, vibrations, charges, and light turned into meaning. To study the invisible is to accept that light and matter speak in probability and nuance, not certainty. Every spectrum, every line, is a message from the molecular world, proof that invisibility is not absence. With the right tools, even the faintest signal becomes a revelation, an entire world hiding in plain sight. Among all the senses that connect us to chemistry, smell is the oldest and most personal. Long before creatures saw or heard, they sensed molecules in water or air, the traces of food, threat, or companionship drifting toward them. Each breath we take continues that ancient exchange. Invisible molecules enter our noses and become sensations, memories, and emotions. A single inhalation can summon decades, turning chemistry into memory and scent into story. Smell begins with volatility. To be noticed, a molecule must escape into the air. It must be small and light enough to drift, yet not so soluble in water that humidity traps it. Volatile molecules strike a balance between attraction and flight, eager to leave their source, but stable enough to last the journey. Once airborne, they ride the currents of breath through the nasal passages until they reach a small patch of tissue high inside the nose, the olfactory epithelium. There, about 400 kinds of receptor proteins wait, each folded into a unique shape. When a matching molecule binds to one, an electrical signal fires. Those signals combine into a pattern that the brain interprets as smell. Unlike vision or hearing, where one receptor corresponds to one frequency or color, the sense of smell works through combinations. Each receptor can respond to many molecules, and each molecule can trigger multiple receptors. The result is a vast combinatorial code, a kind of chemical harmony. With only a few hundred receptors, humans can recognize tens of thousands of different scents. Each one, a unique chord played across the olfactory system. The smell of rain lights up one pattern, freshly cut grass another. To perceive scent is to perform chemical pattern recognition in real time. This process goes deeper than recognition. The olfactory centers of the brain are wired directly into the limbic system, which governs emotion and memory. That's why smells carry such emotional force. They bypass logic and speak straight to feeling. A trace of perfume can recall a person long gone. The aroma of bread can bring back childhood kitchens. The molecules do not care about nostalgia, but the brain translates their arrival into meaning. chemistry has found a shortcut to the heart. Take the scent of rain petrichor, one of the most loved smells on Earth. During dry weather, soil bacteria produce an organic compound called geosmin, which accumulates in the ground. When rain finally comes, droplets hitting the soil release tiny air bubbles that burst upward, scattering geosmin into the air. The human nose is incredibly sensitive to it, able to detect it at concentrations of parts per trillion. That faint earthy note that signals renewal is the smell of microbial chemistry riding on rain. Smell reminds us that our connection to the world is chemical before it is anything else. Every breath is a mixture of molecules entering the body, binding to receptors, and becoming perception. The story of the invisible begins and ends with that exchange. Matter becoming experience, physics becoming memory. The human nose can sense geosmin at levels as low as a few parts per trillion. That means a single drop of it in an Olympic-sized pool would be enough for you to notice. When we breathe in that earthy scent after rain, we are reading a message from the soil life announcing that the land has been watered again. The smell of cut grass tells another quiet story. When plants are wounded by grazing or mowing, they release a blend of molecules called green leaf volatiles, short-chain alcohols, aldehydes, and esters. These aren't random leaks of chemistry. They're signals, warning nearby plants of danger and calling to insects that prey on the creatures feeding on them. To humans, the same molecules smell fresh and alive, the scent of summer itself. It's plant defense reinterpreted by the brain as nostalgia and comfort. The smell of baking bread carries yet another layer of chemistry turned emotion. As dough meets heat, a complex network of reactions unfolds the Maillard reaction, a dance between amino acids and sugars. Hundreds of molecules emerge, including pyrazines, aldehydes, and furans, each adding to that familiar warmth in the air. What feels like home and nourishment is chemistry speaking directly to memory. The molecules drifting through the kitchen don't know what happiness is, yet they evoke it every time. Citrus peels tell a brighter story. Peel an orange and you release bursts of microscopic oil droplets from the skin. Tiny pressurized capsules filled with limonene, pinene, and other terpenes. These molecules evaporate instantly, flooding the air with brightness. Limonene itself is simple in structure, but powerful in effect, triggering receptors that the brain interprets as fresh or clean. It's why so many soaps and cleaning products carry the scent of lemon or orange. The brain doesn't distinguish natural from artificial. If the molecule fits the receptor, the sensation feels the same. In that sense, scent is chemistry's most democratic form. Every molecule has a chance to tell its story. What gives scent its richness isn't just volatility, but the way we interpret it. A smell is not only a set of molecules, but an experience built from chemistry, memory, and context. The same smoke that feels cozy beside a campfire can smell alarming in a kitchen. One person's favorite perfume might make another dizzy. The molecules are identical, only the meanings differ. Our brains write the stories. In perfumery, understanding this chemistry becomes an art. Perfumers, sometimes called noses, train for years to blend hundreds of volatile compounds into balanced harmonies. Some evaporate quickly, forming the top notes that greet you first. Others linger, providing the deeper tones that last. The molecules behave predictably, following physical laws of evaporation and solubility, yet their arrangements evoke emotion, elegance, or longing. Science provides the tools, but art gives them purpose. Our relationship with scent isn't unique to humans. Other species live in worlds painted almost entirely in smell. A dog's nose contains roughly 300 million olfactory receptors, hundreds of times more than ours. They can detect a single molecule of a target substance among trillions of others, following a trail that's hours or days old. Moths can sense a single pheromone molecule released miles away by a mate. Compared to such precision, our sense of smell is modest, yet it has something others may not: emotional resonance. Every whiff connects chemistry to consciousness. Your nose is, in a way, a molecular reporter. It can tell what someone ate for lunch, whether rain is on the way, or if a flower is blooming nearby. It reads the chemistry of the world continuously, storing impressions in memory. Each scent becomes a marker in time, ready to resurface when the same molecules return years later. The fragrance of a rose, the sharpness of winter air, the musk of soil after rain. Each is a conversation between molecules and mind. In scent, we experience proof that matter and memory are never separate. Chemistry speaks, and we remember. Even beyond smell, the air around us is full of invisible chemistry. On the clearest day, it holds countless travelers' droplets, dust, crystals, and molecular clusters so small that billions could fit inside a raindrop. These tiny particles make up the world of aerosols, matter suspended between gas and liquid. They shape clouds, influence weather, and color the sky, all while drifting unnoticed. An aerosol is simply a collection of fine solids or liquids dispersed in air. Fog, mist, sea spray, perfume, smoke, and even your breath on a cold morning all belong to this family. The word itself comes from aero, meaning air, and sol, meaning solution, literally, a solution in the sky. Each particle can range from the size of a dust grain to smaller than a virus. Some fall within seconds, others float for weeks. Aerosols form through two main routes: nucleation, where molecules spontaneously gather into clusters, and condensation, where vapor collects around existing particles. Nucleation is nature's act of creation from almost nothing. Picture humid air, filled with water vapor molecules zipping in every direction. Most of them collide and separate instantly, but sometimes a few stick together long enough to form a stable cluster. If the cluster is too small, it evaporates again, pulled apart by surface tension. Once it reaches a critical size, however, it becomes stable enough to attract more molecules. A droplet is born. From that point, condensation takes over, adding layer after layer of vapor. Surface tension acts like a tight skin around each droplet, resisting expansion. The smaller the droplet, the stronger the tension, which means that tiny droplets need high humidity to survive. Humidity and surface tension constantly negotiate, balancing growth against evaporation. To the naked eye, the air seems still, but at the molecular level, it's alive with these competing forces. Many aerosols form more easily when a seed particle is present, a condensation nucleus. These can be anything from grains of salt thrown into the air by crashing waves, to soot from a candle, or bits of pollen carried by wind. Water vapor clings to these surfaces, condensing more readily than it would in pure air. Without such nuclei, even saturated air might resist forming droplets. Salt crystals are especially powerful seeds. When sea spray evaporates, it leaves behind fine salt grains that drift upward. These hygroscopic particles, literally water-seeking, attract moisture even at low humidity. They swell, forming shimmering droplets that scatter light and soften the horizon. That's why coastal air feels heavier and appears hazy. The ocean's chemistry continues long after each wave breaks. The same principle builds clouds. The sky teems with condensation nuclei, tiny bits of dust, soot, and salt that serve as scaffolding for water vapor. As warm air rises and cools, water condenses on them, forming countless droplets less than 1/100th of a millimeter wide. Alone they are invisible, but in vast numbers they scatter sunlight into the white shapes drifting overhead. A cloud is sunlight bouncing off billions of droplets in suspension. As droplets collide and merge, some grow large enough to fall as rain. Each raindrop is a chemical collaboration between air, water, and dust, a partnership repeated billions of times every storm. Aerosols also shape the color of the sky. Small particles scatter short wavelengths of light, making the heavens blue. When larger particles like smoke or volcanic ash fill the air, they scatter longer wavelengths, turning sunsets red and orange. Even the soft white glow of a hazy afternoon is the work of aerosols diffusing sunlight across the sky. The physics is simple, but the effect feels emotional proof that chemistry can shape beauty without intent. In daily life, aerosols surround us in subtler ways. A spray bottle, a perfume atomizer, the hiss of soda bubbles bursting into mist all create temporary clouds of fine droplets. Steam rising from soup or tea is another form of aerosol, a suspension of tiny water droplets cooling in air. On cold mornings, our own breath reveals itself as vapor condenses into a fleeting cloud. Nature, of course, is the master of this craft. Volcanic plumes, desert dust, forest pollen, and sea spray all feed aerosols into the atmosphere, each influencing climate in its own way. Volcanoes inject sulfur compounds that can reflect sunlight and cool the earth for years. Forest fires send organic particles that seed clouds and alter rainfall. Ocean spray releases salt that not only forms droplets, but also acts as a chemical sponge, cleaning other gases from the air. Through these processes, aerosols quietly regulate the planet's temperature and balance. Some particles warm the air by absorbing light. Others cool it by reflecting it back to space. Each tiny speck plays its part in the planet's equilibrium. There's a subtle beauty in how aerosols blur the boundaries between states of matter. They are neither fully gas nor liquid, neither settled nor entirely free. They exist in the in-between, carrying chemistry upward and downward, linking sea to sky. In their smallness, they hold the power to change weather and color sunsets, to shade the planet or warm it slightly. Each invisible particle is part of a conversation between Earth and air, a quiet reminder that even what drifts unnoticed can shape everything that breathes beneath it. Fog may be the gentlest way air reveals its hidden chemistry. It is a ground-hugging cloud, turning the invisible visible, softening the sharpness of the world. Step into fog, and you pass through millions of droplets, brushing your skin too small to feel, yet large enough to scatter light into a silvery haze. Each droplet acts as a lens, bending and diffusing sunlight into something you can almost touch. The chemistry inside that haze is astonishingly complex. Every droplet holds dissolved gases, tiny ions, and organic molecules gathered from the air. Within these miniature worlds, reactions unfold quietly. Acids form, pollutants transform, and particles trade ions before drifting apart. Fog breathes. By the time it lifts, the air has changed, subtly cleaned and rewritten by its passing. Aerosols and fog teach a humbling lesson. There are no clear borders in nature. Solid, liquid, gas. They are categories for our convenience. In reality, the world is a web of gradients. From perfume mist to mountain clouds, everything mingles and transforms. Even the act of seeing your breath on a cold morning is chemistry made visible, a fleeting union of water vapor and air that dissolves as quickly as it forms. Every droplet floating in the sky is a temporary compromise between forces, surface tension, humidity, attraction, and the gentle pull of light. For an instant, molecules find balance, enough to show themselves, and then they vanish again, returning the air to stillness. The air that holds all of this is incredibly thin. If Earth were shrunk to the size of a classroom globe, its entire atmosphere would be no thicker than a coat of varnish. Yet that thin film of gases performs one of the most elegant balancing acts in nature. It keeps the planet warm enough for water to stay liquid and life to thrive. Without it, the average surface temperature would plunge far below freezing. The oceans would freeze solid, and the story of life would end. The warmth we depend on is the work of invisible chemistry, the greenhouse effect. At first glance, the atmosphere seems transparent. Sunlight streams through easily, carrying energy in visible and ultraviolet wavelengths. The ground and oceans absorb that energy, then re-emit it as infrared radiation, longer wavelengths that carry heat. If all that infrared light escaped freely back into space, Earth would lose warmth almost as quickly as it gained it. But some gases in the air absorb and re-emit this infrared energy, sending part of it back toward the surface. This creates a soft, flexible blanket, not sealed like a greenhouse pane, but breathable and dynamic. It slows the escape of heat just enough to keep the planet comfortable. These greenhouse gases make up less than 1% of the atmosphere. The main ingredients, nitrogen, oxygen, and argon, are almost transparent to infrared light. Their molecular structures are symmetrical. Their vibrations don't produce changing electric fields, so infrared waves slip through them untouched. But molecules like carbon dioxide, methane, water vapor, and nitrous oxide are more complex. When they vibrate, their atoms move asymmetrically, creating oscillating electric fields that interact with infrared light. Each type of molecule resonates with its own set of infrared frequencies, absorbing specific bands of energy. Water vapor is the most abundant and versatile of these gases. It can bend, twist, and stretch in many ways, absorbing heat across a wide range of wavelengths. Carbon dioxide, though much less common, plays a crucial role because it absorbs strongly in regions where water vapor does not what scientists call the atmospheric windows. Methane and nitrous oxide fill in still other gaps, together, creating an invisible filter that controls how heat flows between the surface and space. Like curtains with overlapping patterns, these gases shape Earth's thermal rhythm. The beauty of the system lies in its equilibrium. Each day, sunlight warms the surface. Each night, the Earth radiates heat outward. Greenhouse gases slow that cooling, keeping the world from freezing between sunsets. Without them, our planet would be roughly 33 degrees Celsius colder. The moon, which has no atmosphere, swings from blistering heat by day to deep freeze by night. Venus, by contrast, is smothered under a thick carbon dioxide atmosphere that traps nearly all heat, creating temperatures hot enough to melt lead. Earth sits perfectly in between, wrapped in a thin, balanced blanket usually just right. Scientists describe this exchange using the term radiative forcing, the balance between energy entering and leaving the system. Positive forcing means more energy is retained. Negative forcing means more is lost. Greenhouse gases add positive forcing, gradually raising the planet's stored energy. It's not instant. The warmth builds slowly, like adding extra layers of cloth to a bed until the heat settles in. Water vapor adds a fascinating feedback loop. Warmer air holds more moisture, and that extra moisture traps even more heat. It's not the spark, but the echo, the amplifier of the initial warming. Clouds complicate things further. Thin, high clouds tend to trap heat, acting like greenhouse gases, while thick, low clouds reflect sunlight and cool the surface. The balance between these effects, warming from above and reflection from below, governs much of the planet's climate. Another subtle feedback involves ice and snow. Bright surfaces reflect sunlight, dark ones absorb it. When ice melts, darker ground or water beneath absorbs more heat, melting still more ice. Greenhouse gases nudge this loop along by warming the surface, changing the balance between reflection and absorption. Chemistry, physics, and geometry all participate in this intricate climate ballet. The effectiveness of greenhouse gases depends not only on their abundance, but also on their persistence. Water vapor cycles quickly rising, condensing, and raining out in days or weeks. Carbon dioxide and methane linger for decades. Nitrous oxide lasts for centuries. Each molecule may seem insignificant, but together they form an atmospheric memory, a record of sunlight stored as motion. Over geological time, these gases interact with oceans and rocks, dissolving, reacting, and re-emerging through slow cycles of weathering and volcanism. The carbon dioxide exhaled by a person today may someday become part of a limestone cliff or return to the sky through a distant eruption. Despite its name, the greenhouse effect is not a trap, but a flow, a balance between incoming sunlight and outgoing infrared radiation. With no greenhouse gases, nights would be bitterly cold. With too many, heat would accumulate faster than it could escape. The underlying chemistry, though, never changes. Photons absorbed, bonds stretched, energy exchanged, and light re-emitted in the darkness above. Each molecule's infrared behavior is remarkably elegant. Picture its atoms connected by springs. When light of the right wavelength passes by, those springs vibrate in sync, capturing the photon's energy. The molecule later releases that energy, sending a new photon outward in a random direction. Some of those photons head into space, others back to the ground. At any moment, the atmosphere glows faintly in infrared light, a constant, invisible conversation between Earth and sky. Sunlight speaks in short wavelengths. The Earth replies in long ones. Greenhouse gases act as translators, repeating part of the message downward. The planet stays warm, not because energy is trapped, but because it is exchanged, delayed, and redistributed. The atmosphere breathes, absorbing, emitting, balancing. The same chemistry that keeps nights mild also drives clouds, fuels photosynthesis, and keeps the oceans liquid. It's not a villain or a miracle, just a mechanism tuned by time. High above this living layer, sunlight and oxygen perform a different kind of alchemy. Invisible ultraviolet rays strike oxygen molecules, splitting them into single atoms. These lone atoms drift until they collide with intact oxygen molecules, forming ozone, 3 atoms bound in a fragile triangle. With that simple rearrangement, ordinary oxygen becomes something entirely new, a guardian. In the stratosphere, ozone absorbs much of the sun's ultraviolet radiation, the kind that can damage DNA and break chemical bonds. Ozone is constantly made and destroyed. Ultraviolet light both creates it and tears it apart, maintaining a self-regulating cycle. Each molecule lasts only minutes before breaking, yet the overall layer persists, a shimmering shield stretched around the planet. It absorbs harmful radiation, allowing only gentler light to reach the surface. Closer to the ground, ozone tells a different story. Here, it forms through pollution, sunlight, and reactive gases mixing in the wrong place. The same reactivity that protects life high above can irritate lungs and plants near the surface. Ozone becomes a symptom of imbalance, not a savior. Behind both stories, the protective ozone above and the pollutant below, lies a restless kind of chemistry driven by radicals. A radical is a molecule or atom with an unpaired electron, a small imperfection that makes it extraordinarily reactive. These species live briefly, sometimes for only a fraction of a second, but they guide much of the atmosphere's chemistry. The most important of them is the hydroxyl radical, written as OH, often called the atmosphere's detergent. It reacts with nearly every pollutant it meets, stripping electrons and reshaping molecules into forms that dissolve in rain or settle harmlessly to the ground. Hydroxyl radicals form when ultraviolet light interacts with ozone or water vapor, splitting molecules into energetic fragments that immediately seek partners. Once created, OH radicals begin a cascade oxidizing carbon monoxide into carbon dioxide, breaking down methane and cleansing volatile organic compounds. This invisible housekeeping happens every moment. Without radicals, the air would stagnate, filling with gases that never decayed. Smog would linger indefinitely. Natural balance would erode. The atmosphere, through this chemistry, cleans itself. Light, air, and motion combine in an endless cycle of creation, destruction, and renewal. Nitrogen oxide's molecules born from the marriage of nitrogen and oxygen are among the most restless of atmospheric players. Chemists bundle them together under the shorthand NO, a collective name for nitric oxide, NO, nitrogen dioxide, NO, 2, and their reactive kin. They shuttle between these forms with every turn of the day, driven by sunlight, temperature, and chance. When daylight strikes, photons split nitrogen dioxide into nitric oxide and a free oxygen atom. That free oxygen quickly joins another oxygen molecule to create ozone. As night returns, the chemistry shifts again. In the cool dark, these reactive gases form nitrates and peroxyacetyl compounds that dissolve into dew or settle as aerosols. Every dawn resets the rhythm, a continuous, light-driven dance between creation and decay that defines the living chemistry of the lower atmosphere. Organic radicals join this performance as unpredictable partners. Peroxy Rho 2 and alkoxy radicals arise when hydrocarbons released from forests, fuels, or fires encounter the hydroxyl radical, the atmosphere's tireless cleaner. These carbon-centered radicals are the intermediates of smog chemistry, passing oxygen atoms between them like dancers exchanging partners on a crowded floor. Sometimes their reactions lead to purification, converting pollutants into harmless products. Other times, they build more ozone or create fine particles that cloud the air. The outcome depends on a delicate balance, the intensity of sunlight, the ratio of hydrocarbons to nitrogen oxides, and the temperature of the day. The sky, it turns out, is a giant reaction vessel, dynamic, reactive, and self-correcting. Despite their volatility, radicals are not villains. They are the system's custodians, breaking down what the world produces and returning it to simpler forms. They move invisibly, unmeasured, except by the traces they leave behind. You can sense their work in the metallic tang that follows lightning, in the way the air clears after rain, in the faint haze over a busy city that vanishes when the wind turns. They are chemistry's invisible workforce, endlessly rebuilding and refining the sky. Lightning itself is one of the atmosphere's most spectacular chemists. A single bolt can heat the air to more than 30,000 degrees Celsius hotter than the surface of the Sunday. In that instant, nitrogen and oxygen molecules are torn apart, forming reactive nitrogen oxides that later drift downward and dissolve into raindrops. Each storm, then, is not just meteorology, but also biochemistry, a burst of natural fertilizer returning to the soil. In seconds, lightning turns atmospheric calm into chaos and back again, seeding new life with the remnants of its violence. The life of a radical is astonishingly brief. A hydroxyl radical, for instance, lives less than a second before it reacts. But multiplied across the entire atmosphere, these momentary events sum into vast transformations. Every instant, trillions of radicals oxidize carbon monoxide, dismantle methane, and cleanse organic vapors, maintaining the delicate balance of breathable air. Their combined choreography keeps the atmosphere stable and self-renewing, a continuous pulse of chemical life. Smog is where this invisible chemistry becomes visible. In cities, the air becomes a living laboratory. Morning traffic pumps out nitrogen oxides and hydrocarbons. As the sun climbs, its photons awaken the hydroxyl radicals, setting off reactions that shuffle oxygen and carbon atoms into new forms. Ozone builds up during the bright hours, mixing with fine aerosols and creating that familiar bluish haze. By evening, when sunlight fades, the chemistry quiets and cooler air restores equilibrium. Smog may look like pollution, but chemically, it's a moment in a much longer process, an atmosphere at work, cleaning and recycling itself. Each molecule of ozone or peroxide eventually breaks down into stable compounds: carbon dioxide, water, nitrates, and dust. What we perceive as disorder is often chemistry mid-conversation. High above, in the stratosphere, ozone chemistry follows a different rhythm, but obeys the same principle of balance. Ultraviolet light splits oxygen molecules into individual atoms. Those atoms collide with other oxygen molecules to form ozone. A moment later, slightly weaker ultraviolet light breaks ozone apart again. The two reactions happen almost equally fast, maintaining a steady ozone layer that absorbs harmful radiation while allowing visible light to pass. This fragile equilibrium is one of Earth's great achievements, a self-sustaining shield born of sunlight and air. Small disruptions can tip that balance. Chlorine and bromine atoms, released from human-made compounds like chlorofluorocarbons, catalyze ozone destruction by providing alternate reaction pathways. For decades, they thinned the ozone layer, especially over Antarctica. Yet global cooperation and chemistry itself have begun to repair the damage. Those destructive compounds are declining, and satellites now record slow but steady recovery. It is chemistry, healing chemistry. If there is one unifying truth in all this, it's motion. Molecules collide, split, and recombine endlessly. Ozone forms and fades, radicals appear and vanish. Through it all, the atmosphere stays remarkably steady, a system whose balance comes not from stillness, but from perpetual change. Above every landscape, the air hums with invisible action. The calm sky is an illusion. Every second, billions of reactions flash and fade, maintaining the breathable world below. From this restless chemistry arises one of nature's most profound illusions: transparency. It seems like nothing at all, a lack of color, an absence of obstruction. But to be transparent is an achievement of exquisite molecular precision. For light to pass unhindered through matter, the electrons in that matter must neither absorb nor scatter it. They must hold on just tightly enough to resist excitation, yet not so tightly that they disturb the wave as it moves. Transparency, in short, is cooperation. When light meets matter, three possibilities exist: absorption, scattering, or transmission. Absorption occurs when a photon's energy matches the gap needed to excite an electron to a higher state. Scattering happens when light bounces off irregularities, atoms, defects, or particles, sending it in new directions. Transmission, the rarest case, happens when neither dominates. The light glides through as if the material weren't there. Transparency is therefore not emptiness, but balance. Matter and light, agreeing on terms of passage. At the atomic level, this balance is dictated by electron structure. In solids, atoms share electrons across energy bands, broad zones where electrons can move. Between these bands lie forbidden regions, or band gaps. If a photon's energy is less than the gap, it cannot excite an electron, and so the photon continues, unabsorbed. If the photon carries more energy, it is absorbed and lost. Glass, quartz, and pure water are transparent because their band gaps are wider than the energy of visible light. Ultraviolet photons, being more energetic, can bridge those gaps and are absorbed, hence UV protection in windows and sunglasses. Metals, by contrast, are opaque because their electrons move freely in partially filled bands. They absorb or reflect nearly every photon that touches them. Transparency exists only where light finds no resonance in matter's inner architecture. But even if absorption is avoided, scattering can still intervene. The blue of the sky, the whiteness of clouds, the milkiness of fog, all arise from scattering. Tiny particles smaller than the wavelength of light produce Rayleigh scattering, which favors shorter, bluer wavelengths. That's why the sky glows blue and sunsets blaze red. When particles are closer in size to the wavelength, scattering becomes wavelength independent, known as Mie scattering. That's what makes clouds white. Droplets in a cloud scatter all colors equally, blending them into brightness. To achieve true transparency, a material's internal structure must be uniform at scales smaller than the wavelength of visible light, hundreds of nanometers. Glass achieves this by being neither liquid nor crystalline. When molten silica cools quickly, its atoms freeze in random positions, forming an amorphous solid with no repeating lattice to deflect light. The result is a medium smooth enough that photons glide through unbothered. Crystals like diamond or quartz can also be transparent, but for the opposite reason. Their atomic lattices are so perfectly ordered that light waves pass coherently, scattering just enough to continue forward in phase. In either case, transparency is harmony atoms, moving aside in perfect rhythm to let light through. Refraction, the bending of light as it moves between media, adds another layer to the story. When light slows down in a denser substance, its direction changes. The degree of bending is set by the refractive index, a measure of how much light is delayed. Glass bends light enough to form lenses. Water bends it modestly, making a straw appear crooked. Diamond bends it intensely, splitting white light into rainbows of fire. Transparency isn't the absence of control, it's control perfected. Reflection is transparency's mirror twin. At every boundary where materials of different refractive indices meet, some fraction of light bounces back. Even the clearest window throws a faint ghost image of the room behind you. Reflection grows stronger when the contrast between materials increases. A wet street gleams because the layer of water atop asphalt changes the boundary conditions, turning the surface into a temporary mirror. Every reflection is an echo of light negotiating its way between worlds. Water offers a living demonstration of selective transparency. In shallow pools, it seems clear, but as depth increases, colors vanish in order. Red light is absorbed first, then orange and yellow. Only blue penetrates to great depths. The sea's color is thus not just reflection, but absorption, sculpted by physics. Infrared light is absorbed as heat. Ultraviolet disappears into electronic excitations. The visible spectrum, the middle child of energy, is the one that survives, allowing sunlight to reach the underwater forests that feed the planet. Plastics tell a more fragile version of the same story. Their polymer chains, tangled threads of carbon and hydrogen, possess energy gaps too wide for visible light. But impurities or crystalline patches can scatter photons, turning clear plastic cloudy. Over time, exposure to light breaks bonds, forming tiny defects that yellow and haze the material. Transparency, it turns out, is perishable. Nature makes its own transparent wonders. Pure ice, when free of bubbles and cracks, can rival glass in clarity. Yet snow made of countless tiny ice crystals appears white because each boundary scatters light. The difference lies not in composition but in structure. Smooth the surfaces, and clarity returns. Roughen them, and light dissolves into opacity. The line between clear and cloudy can be a few nanometers wide. We tend to think of transparency as simplicity, but it is anything but simple. A cubic centimeter of glass contains 10 quadrillion atoms, each obeying quantum laws, each interacting with light in perfect coordination. The fact that we can see through such density is astonishing, a collective act of atomic courtesy. When light passes through, it doesn't travel unimpeded. It slows, interacts, and resumes. Electrons oscillate, absorbing and re-emitting photons in sync so quickly that the process seems instantaneous. The apparent smoothness of transparency hides billions of microscopic negotiations every second. So, when you gaze through a window, you're witnessing a treaty between matter and light, a momentary understanding that allows vision to cross from one side to the other. The glass doesn't ignore the light, it guides it. It bends, delays, and returns it intact. Diamonds dazzle by scattering, water calms by letting light glide through, and air, in its perfect uniformity, disappears altogether. Transparency isn't the absence of interaction, it's the perfection of it, a quiet contract between photons and atoms that makes the visible world possible. For most of history, transparency was a gift found in nature, a property of quartz, water, and glass. Humans could shape it, polish it, and admire it, but not truly design it. In the past century, that changed. Science began to treat light not as something to observe, but as something to engineer. Where nature achieved transparency through stillness and simplicity, humans learned to shape invisibility through precision. The effort has transformed how we build, see, and even protect ourselves. The story begins at the scale of the very small. Nanoparticles, tiny structures smaller than bacteria, obey rules different from bulk materials. On this scale, light behaves strangely, bending and scattering in ways that no simple lens can predict. Gold, a metal we think of as stable and yellow, turns ruby red when its particles shrink to a few dozen atoms across. This transformation comes from a phenomenon called plasmonic resonance. In metals, electrons move freely, and when light strikes a tiny particle, those electrons vibrate together at specific frequencies. Depending on size and shape, the particle will absorb some colors and reflect others. Medieval artisans unknowingly used this principle in stained glass, mixing gold and silver nanoparticles into molten glass to create glowing reds, greens, and yellows that still shine in cathedral windows. Modern scientists use the same principle with precision instruments. By adjusting the geometry of nanoparticles, researchers can design materials that reflect, absorb, or transmit specific wavelengths. Plasmonic nanoparticles can convert light to heat with remarkable efficiency. In medicine, that property allows targeted cancer treatments. Nanoparticles absorb light and warm tumor cells without harming the tissue around them. In another direction, these same particles concentrate light into regions smaller than a wavelength, enhancing the sensitivity of sensors capable of detecting single molecules. It is chemistry turned choreography, electrons and photons moving in concert, performing on a scale far below what eyes can see. Quantum dots take this control further. These are semiconducting crystals so tiny that their behavior follows quantum mechanics. When they absorb energy, they re-emit light of a specific color that depends entirely on their size. Smaller dots glow blue, larger ones shine red. Adjusting the dot's diameter by just a few atoms can change its color entirely. Today, this precision underlies many modern displays. Televisions and monitors use layers of quantum dots to transform backlight into pure, vivid colors. Instead of relying on dyes or filters, they depend on the quantized steps of electron energy. It is light tuned by design, a fusion of physics and craftsmanship. Thin films expand the palette even further. When light reflects from several layers only a few hundred nanometers thick, the waves overlap, sometimes canceling, sometimes reinforcing one another. The result is iridescence, the same effect that paints soap bubbles, butterfly wings, and oil slicks in liquid rainbows. Engineers have learned to control this interference deliberately. Anti-reflective coatings on eyeglasses and camera lenses use stacks of such films to cancel glare. Solar panels use them to reduce reflection and capture more energy. Some materials now absorb light so thoroughly they seem to erase themselves, appearing as voids rather than surfaces. These super black coatings rely on forests of nanostructures that trap photons through countless reflections, giving them no escape path. The effect is visually disorienting, a hole in reality sculpted from geometry. The most ambitious step, however, comes from metamaterials engineered structures designed to bend electromagnetic waves in ways nature never intended. Their power lies not in chemistry, but in architecture. Tiny repeating elements, loops, rods, or spirals act as antennas that interact with light at sub-wavelength scales. By arranging them in patterns, scientists can give the material properties not found in any natural substance, including negative refractive index. In such materials, light curves backward, wrapping around objects instead of striking them head-on. The idea was proven in the early 2000s. and caused astonishment. In theory, light could be guided around an object and recombined behind it, making the object effectively invisible. These invisibility cloaks are real, though far from perfect. Early versions worked only for microwaves, not visible light, and only when viewed from limited angles. Visible light's shorter wavelength makes it vastly harder to manipulate. Even so, progress continues. Researchers have created cloaks that hide microscopic objects, redirect heat flow, or bend radar signals around an aircraft. True invisibility, the kind that would let someone disappear entirely, remains a dream. But the fact that light can be coaxed to take such paths at all feels like victory enough. Metamaterials now serve many purposes beyond illusion. They enable super lenses that capture details smaller than the wavelength of light, breaking what once seemed a fundamental limit. They steer radar waves for stealth technologies, improve antenna efficiency, and manage heat in microelectronics. Each of these rests on the same foundation: geometry controlling light. Humans, it seems, have learned to sculpt the invisible. There is something poetic in the contrast between nature and invention. Nature's transparency relies on simplicity: glass, water, and air let light pass by, avoiding interaction. Human-made invisibility, by contrast, depends on complexity. Light interacts constantly, but the interactions are orchestrated so perfectly that the eye cannot tell. One is serenity, the other is strategy. Both show that light is persuadable. It can be bent, delayed, or rerouted with care. In mastering this conversation between matter and light, humanity has not defied nature, but joined its dialogue. Beyond laboratories and cloaks, these discoveries shape daily life in quieter ways. Modern surfaces, screens, and fabrics are built from nanoscale engineering, tiny work that produces large comfort. Take sunscreen. For centuries, protection meant covering skin with thick white paste made of zinc oxide or titanium dioxide. These minerals scattered ultraviolet light effectively, but also made faces ghostly pale. When the same materials were made into nanoparticles a few billionths of a meter wide, everything changed. They still blocked ultraviolet rays, but because the particles were smaller than the wavelength of visible light, they no longer scattered it. The lotion became transparent, forming an invisible barrier that reflects harmful light while letting ordinary sunlight pass through. Nanotechnology, in essence, taught sunscreen how to disappear. These invisible defenders are carefully tuned. Their size determines which wavelengths they scatter most. Too small, and they lose effectiveness. Too large, and they become visible again. The result is a delicate balance: small enough to vanish, large enough to protect. The particles don't absorb light or heat up. They simply redirect ultraviolet radiation away from the skin. Modern sunscreens owe their clear, comfortable texture to chemistry that operates below the threshold of sight. The same principle extends to the surfaces around us. Car, windshields, eyeglasses, camera lenses, and even bathroom mirrors carry nanoscopic coatings that repel water and resist fog. These rely on hydrophobicity, the tendency to repel moisture. On a smooth surface, water spreads into a film, causing fog and streaks. But on a surface textured at the nanoscale, droplets can't spread. They sit like beads and roll away with gravity. The effect, called the lotus effect, mimics the leaf of the lotus plant, whose microscopic bumps and waxy coating keep it clean in muddy ponds. Now this principle protects skyscraper windows, solar panels, and clothing fabrics, turning rain into a self-cleaning mechanism. Even swimming goggles use a version of it. spreading moisture into layers so thin that light passes through without distortion. Electronics tell another chapter of the nanoscale story. Every chip, phone, and display today is built at dimensions measured in nanometers. Circuits once etched in millimeters now count. Features smaller than viruses. Transistors switch faster than neurons, moving electrical signals through patterns only a few atoms wide. Shrinking these components has not just made devices smaller, it has made them smarter and more efficient. The invisible design of the modern world lives in the spaces between atoms. Quantum dots, the same technology that powers vivid television displays, also appear in laboratories as tools for sensing, imaging, and medicine. Their light emission changes with environment, allowing scientists to trace reactions, detect toxins, or mark cancer cells under a microscope. Nanostructured materials can now detect single molecules of gas or trace pollutants in water. A thin layer of gold or graphene on a sensor can amplify signals so sensitively that one breath may reveal early signs of disease. These instruments act like invisible laboratories, constantly analyzing air and water around us. Yet, the smaller we build, the more caution we need. Nanoparticles are reactive by nature. Their high surface area and tiny mass let them interact with biological systems in ways larger materials cannot. Most, like those in sunscreens or coatings, are designed to be inert, insoluble, non-reactive, and easily washed away. Others are deliberately functional, carrying drugs, capturing heat, or binding to specific molecules. Responsible nanotechnology demands understanding as much as invention. Scientists track how nanoparticles move through ecosystems, how they cluster or dissolve, and how they affect living tissues. The goal is balance, to use the benefits of smallness without courting its risks. In medicine, this precision becomes an art. Nanoparticles can be engineered to deliver drugs directly to where they are needed, reducing side effects. Some are built to recognize markers on diseased cells, releasing treatment only at the target. Others slip through biological barriers that ordinary molecules cannot cross, bringing therapy to otherwise unreachable places. Each is a courier, working on the smallest scale imaginable. The goal is gentleness through control, healing through precision rather than power. Nanotechnology reaches even into our clothing and homes. Fabrics woven with nanosilver resist bacteria and odor. Sportswear made from nanofibers stays breathable while repelling moisture. Paints and varnishes contain nanoceramics that resist scratches and fading. None of these look unusual. They simply work better, last longer, and quietly serve their purpose. The world's surfaces have not changed in appearance, but their chemistry has become more intelligent. The most extraordinary thing about this revolution is its invisibility. The coatings on your glasses, the nanoparticles in your sunscreen, the quantum dots in your television, they all exist beyond sight, yet define how the world feels. They make colors richer, air cleaner, materials more durable, and daily life smoother. Every unseen particle is part of a quiet collaboration between human curiosity and atomic structure. There is grace in how the smallest things accomplish the greatest ease. A film a few nanometers thick can make a window shed rain, a screen shine brighter, or skin stay safe under a summer sun. It's chemistry turned into comfort, and though invisible, it speaks to one of the most human desires to make the world both safer and more beautiful through understanding. We now live surrounded by these unseen helpers, the fruits of centuries spent learning how light, matter, and motion intertwine. Between the transparency of air and the invisibility of technology lies the story of modern life. light-guided, matter persuaded, and perception refined until the invisible feels natural. The boundaries of vision are no longer dictated by nature alone. They are built, tuned, and improved by design. And that, perhaps, is the quiet wonder of the age of the nano, an era where the invisible has become humanity's most visible achievement. Technology has learned to whisper. The nano world doesn't shout for attention. It edits reality with the precision of a poet, refining rather than overwhelming. It is the science of restraint, the elegance of smallness, sunscreens that vanish on the skin, coatings that make glass self-cleaning, displays glowing with impossible color. All of them are evidence that mastery over the invisible has become an art form. The future may bring new applications and new dilemmas, but the principle remains the same. The smallest actions can create the greatest comforts, and the quietest chemistry can change the loudest parts of life. If you could pause the world, suspend scent, sound, and movement, you'd find that almost everything around you is born of invisible chemistry. The aroma of food, the rhythm of breath, the smell of rain, even the warmth of a human touch, each arises from exchanges of molecules, electrons, and energy too small to see. The visible world is merely the surface of an ongoing molecular conversation, centuries old, ceaseless, and unbroken. Nowhere is that conversation more familiar than in the kitchen. It's the most democratic laboratory on Earth, where every meal is an experiment and every aroma a data point. Fermentation, for instance, is invisible chemistry made tangible. Beneath the rising dough of bread or the tang of yogurt thrives a microscopic civilization of yeast and bacteria. They feast on sugars, releasing acids, alcohols, and gases. Each bubble of carbon dioxide in a loaf of bread is yeast's silent breath, an echo of the same respiration happening in your own cells. When dough rises, it's not magic, it's metabolism. Then comes the Maillard reaction, the symphony of browning. When heat strikes a mixture of proteins and sugars, they rearrange into hundreds of new compounds, producing the roasted aroma of coffee, the caramel hue of baked bread, and the savory crust of a seared steak. It begins invisibly, with electrons shifting, bonds breaking and reforming, and water slipping away. The golden glow on your toast is chemistry, revealing its hand only at the finale. Even the scent of food traveling through a room is a diffusion experiment. Tiny volatile molecules escape the pan, bounce through air, and land on receptors deep in your nose. One sniff is the sum of thousands of collisions, a slow migration of invisible messengers transformed into memory and appetite. The warmth of a kitchen, the comfort of spice, the joy of flavor, all of them arise from unseen chemical choreography. That same choreography hums inside your body. Every breath you take is a quiet exchange of gases across microscopic membranes. Oxygen enters, carbon dioxide leaves, and hemoglobin ferries molecules like an orchestra of precision. The carbon you exhale will one day feed a leaf. The oxygen you inhale was released by one. The cycle is ancient and silent, a planetary exhalation shared by every living thing. Within your cells, still smaller dramas unfold. Neurotransmitters flicker between neurons in microseconds. Dopamine lighting, anticipation, serotonin balancing calm, acetylcholine carrying command. Each molecule exists for seconds before being reabsorbed or dismantled. Thoughts themselves are built from these invisible transactions. Hormones extend this conversation in slower rhythms, chemical messengers drifting through blood to regulate hunger, sleep, fear, and love. Adrenaline sharpens focus, melatonin softens awareness, oxytocin dissolves loneliness. You are not just a mind housed in matter. You are matter in constant, invisible negotiation with itself. Even emotions, which feel so grand and abstract, are small-scale events in chemistry. Joy is a cascade of molecules. Calm is a quiet reduction in cortisol. Connection is a molecular bloom across synapses. Every sigh, heartbeat, and moment of peace is chemistry keeping time. Step outside, and the invisible expands to planetary scale. The air is alive with unseen labor. Soil, microbes, fix nitrogen, turning the inert gas that fills most of the atmosphere into compounds plants can use. Without them, the green of the world would vanish. The smell of earth after rain, the scent we call petrichor, comes from a molecule named geosmin, released by these same bacteria as they stir to life. It is one of the rare moments when the invisible announces itself. Rain amplifies this chemistry. Droplets fall through air, sweeping up ions and dust, releasing faint electric charges that ionize nearby molecules and sharpen scent. Lightning adds its own punctuation, splitting nitrogen and oxygen, creating radicals that cleanse the air. Each storm is both weather and reaction, a planetary rinse cycle renewing balance molecule by molecule. The oceans participate too. When waves break, they fling droplets of seawater into the air. As those droplets evaporate, they leave salt crystals behind microscopic seeds that help form clouds. Each cloud is born from a marriage of ocean spray and sunlight chemistry woven into meteorology. What we call weather is a grand-scale chemical system stretching from seabed to sky, powered by invisible exchanges. Even light and color themselves are chemical negotiations. Pigments glow because their molecules absorb and scatter particular wavelengths. Glass is transparent because photons find no reason to stop. The blue of the sky comes from air molecules scattering shorter wavelengths more than longer ones. Vision itself, seeing the sky at all, is chemistry in action. Photons striking retinal molecules, twisting them, and triggering cascades of electrical impulses that your brain translates into color and shape. What you call sight is the transformation of invisible energy into meaning. If you could shrink down to molecular scale, the illusion of stillness would dissolve. Air would churn with collisions. Solids would tremble with vibration. Liquids would ripple with ceaseless motion. The table under your hand, the breath in your lungs, even your own thoughts would appear as storms of energy. Stillness is simply motion, too small for eyes to register. Chemistry makes no distinction between the profound and the ordinary. The same physical laws that fuse hydrogen in stars caramelize sugar in your kitchen. The same principles that drive the metabolism of a cell sculpt the weather of a planet. Whether in a nebula or a teacup, matter follows the same quiet choreography. It is nature's universal syntax, the way atoms speak to one another through time. Yet for all its ubiquity, we forget it. The world feels solid, visible, stable, but beneath every surface, the invisible continues its work. Atoms bind, break, and bind again in infinite patience. The glass you drink from is not frozen stillness, but a slow, vibrating sea of molecules. The air that feels calm is a swarm of collisions, moving faster than sound. You live inside a masterpiece of invisible equilibrium, Every drop of water, every breath of air, every heartbeat is a reminder that visibility is the rare exception. What you can see is merely the echo of what you cannot. Steam curling from a pot, rain beading on glass, sunlight scattered in the air. Each is a translation of invisible order into sensory experience. Molecules push, pull, bend, and twist, creating the illusion of a still and solid world. We exist in a clear vessel filled with motion. Beneath its calm surface, chemistry sustains everything steady, uncomplaining, eternal. Its constancy is so familiar that it becomes invisible twice, first to the eye, then to the mind. The air in your lungs, the glass in your window, the warmth on your skin, all depend on molecular cooperation we never notice. The unseen is not absence, it is structure. It holds the visible together. A breath of air is a miracle of ratios, oxygen and nitrogen mixed with exquisite precision. A glass of water is a lattice of hydrogen bonds, forming and breaking billions of times per second. Every cloud, every scent, every spark of flavor is a whisper between molecules. What looks still is only movement slowed to comfort's pace. Even the solid table hums with atomic vibration, and your body, steady and warm, is a web of electrons, protons, and enzymes dancing in silent synchrony. This chemistry never rests. It doesn't demand notice, only balance. There's something profoundly reassuring about that. The universe isn't held together by force or chaos, but by conversation, a patient dialogue among invisible things. Molecules meet and part, atoms rearrange, bonds stretch and release. Out of their motion comes stability, out of their stillness, life. When you inhale, the oxygen entering your lungs was forged in a long-dead star. When you exhale, the carbon dioxide you release may one day nourish a leaf, dissolve into the sea, or freeze in a far-off cloud of ice. Chemistry is the great recycler, turning matter into continuity. It erases the boundaries between living and non-living, between flame and heartbeat. The spark in a neuron is kin to lightning across the sky. The energy in your pulse is a quieter version of the sun's fire. Perhaps that is the final truth of invisibility. It isn't about hiding, but about harmony. We don't see molecular order because it doesn't need to be seen. It is so reliable that we mistake it for silence. Water stays liquid because hydrogen bonds form and break with perfect rhythm. The air stays breathable because radicals, ozone, and sunlight negotiate balance without fail. The invisible world is not chaotic, it is serenity written in motion. If the visible world is a stage, the invisible is the crew behind the curtain. Microbes, molecules, and forces maintaining the performance without applause. Even as you sleep, oxygen diffuses through your lungs. Dew condenses on leaves. Enzymes hum in your cells. The quiet chemistry of existence continues, asking nothing in return. To be invisible, in the truest sense, is to be trustworthy. Processes that never fail no longer need to announce themselves. The more harmonious a system becomes, the less it demands to be noticed. That is as true for atoms as it is for life. The unseen is not a mystery to be solved, but a piece to be understood. And so, as this journey through invisible chemistry comes to rest, remember, every sip of water, every breath of air, every scent of rain is a conversation billions of years in the making. The molecules that shape your world have wandered through stars, oceans, and lungs before reaching you. To live is to join their story. The invisible is not the opposite of the visible, it is its foundation, its quiet heart. The next time you see steam rise or light bend through glass, pause for a second. Beneath that moment lies a universe of silent coordination. The air you breathe has circled the planet countless times, brushed through forests, crossed oceans, passed through hearts and storms alike before reaching you. Every breath is an act of connection, an exchange between the visible and the unseen.